Maybe not. Welcome Engineering Statics. This is ENGR ampersand 214 at Bellingham Technical College. And the topic of this lecture is distributed force systems. Up till now, with the exception of maybe the very tail end of special force systems, all of our forces and moments have basically been something that's applied at a single point and in a single line. So now we're going to kind of expand that out to 2D and 3D. And we're going to look at instances where there isn't a single point of contact of a force and then a resultant moment that we can calculate. We're going to look at what are called distributed forces. So these come in two flavors. One is a surface distributed force and the other is a body, and these have very practical applications all over the world of engineering. So surface forces, these are things like air pressure and water pressure. So if you have something underwater, like at the bottom of a tank holding that water pressure, the pressure exerted by that fluid, that hydrostatic pressure, is a distributed force over the surface of whatever you've made the tank out of. Both pneumatic and hydrostatic fall in that category. They act on a surface over its whole area. You can have surface charges if you're working with an electrical system. So the repulsive effect of positive, negative charges will act on surfaces and all over the surfaces. You can have distributed forces that act over the entire volume of your body, your rigid body that we're evaluating here in statics. Most common one that we've already looked at is weight. Gravity is a distributed force, or it induces a distributed force system that results in acceleration. So that doesn't just act on the surface, it acts all over the body, and we very often look at that distributed force as its resultant acting at the center of mass. Another body volumetric distributed force that you might encounter, depending on what you're doing, is magnetic. So unlike surface charges and electrostatics, magnetics act like distributed forces act like gravity, so all over the body. As a warning, this topic is going to be the first time that we have to whole hog deploy some calculus just to get our hands around things. Unfortunately, the idea of a distributed force is where we really have to make that leap from algebra to calculus. Hopefully all of you all have completed some studies of at least differential calculus, and you understand the concept of a derivative. If you have not integrated, I will tell you right up front, the definition of an integral is the function for which, if you took its derivative, you would get what's in the integral. So that's actually how you calculate it. It is you can think of it as an antiderivative. And we'll have very, very simple functions in this course for statics, so it will not be hard to take a look at the function and say, if I took the derivative of something, what would I have to take the derivative of to get that? We'll be looking at polynomials and maybe some trig functions for which you should understand the derivatives of really well. What we're really going to dive into is the applied principle of an integral as a summation over a continuous function. So we're going to think about integrals as a continuous sum of very, very small bits of force or very, very small bits of moment due to those forces. So that's the practical definition of an integral, and that's what we're really going to lean on. And then when we actually go to calculate them, hopefully we'll just have some easy functions that we can turn the crank on. So why do we need to do that? Well, mainly because there is no practical way, if we had a distributed load like you're seeing here in this figure, to actually get an equivalent resultant. We don't know what it is in any particular place. We know there's one somewhere. We could, if we knew how to do it, we could get the full equivalent resultant force as F sub r, capital F sub r here, that represented the action of this force per unit length. This is a linear distributed load, and it varies. It's nothing here at x equals 0, and then it goes up, and so by the time you get to this point along our x-axis, which could be maybe a beam or some kind of linear structure, it's reasonably high. And remember, this is a force per unit length. So it isn't a single point force. So it's dependent on where you are. And so, then it goes down, then it goes back up again. So if we wanted to know what was the total downward force, if this were a beam, say, we would need to add up the force per unit length here and here and here and here, all the way to the end of where the application point is. And unfortunately, it's varying continuously with X. We don't have one portion that is a single level and that steps up or steps down. It's constantly changing. And it's that continuous change that launches us into the world of needing to use an integral to add it all up, literally. So let's go through the mechanics of how we add up little tiny bits of something of interest. So we're going to zero in on this little itty bitty slice of our load distribution. So we're gonna look at a little bit of a width of our theoretical beam, or our distance along the x-axis, and we're going to call it dx. So those of you who remember your calculus, d means a tiny bit, a differential element. So this is a little width on the x-axis that's infinitesimally small, really tiny. Well, just doing a units balance, if f of x, and this is a function of x, so this is function notation, if our load per unit length is some function of x, so it's up here on kind of on the y-axis, and we're looking at an x distance of dx, we know that the actual load, like in newtons say, for this little tiny element is the area under this little tiny slice, so this little rectangular slice, right? So we could take, to get the area, we could say, well, we could take the y point, which is f at whatever point we are, and it changes at every point, and then multiply by the width. Because this is approximately a rectangle, because it's so small, the change in x or in the y point at this corner and this corner is negligible. So that's the big power of using a tiny slice. We can define a very simple area element or volume element if we're doing it in 3D. And this is in fact this idea of a simple approximation that is valid for a tiny slice. This is actually the basis of finite element analysis, which many of you who are going into mechanical or civil will use on a daily basis probably. So here you are. So if our force distribution, which is a function of x, say is in newtons per meter, we've now got newtons per meter, our y point here, times meters, differential element of length. X is in length. So there's our force for that little bit. Well, if we want to know the total force over the entire length of the beam, or width of the beam we'll call it, from x equals 0 to x equals L here, all we have to do is add up every one of these infinitesimal little bits. And that's where we use an integral. And that's where we use its kind of definition as a summation of an infinite number of infinitely little bits. That's one way of thinking of an integral. So we're going to add up the force due to each one of these little dx, differential of x width slices, at whatever value they are on your load distribution point, and we're going to add them up from x equals 0 all the way to x equals L. Okay, so let's just write this out using what we already know about vectors, because this does have a direction, and it's good to keep track of that. So our load distribution function in newtons per meter, say, and I'm going to keep units, I'll go ahead and use metric units, because we can use those units to make sure we've done the integral and the summation right, and we didn't make a mistake, and it helps us think of what we're doing. So here's our load distribution function as a vector. If my y-axis is in the j hat unit vector direction, I can write this as negative f, which is the magnitude of the load distribution function at any point, times j hat, the unit vector in the j direction, because it's got a negative because it's pointing down. And so my lowercase f is really a function of x. And I don't know what it is. It's some crazy function. But it's continuous, and we're going to assume it's differentiable so we can integrate it. Very important. There's no abrupt changes. There's no missing points at which we couldn't define a derivative. Okay. The force due to our element dx that we just defined here can be written, of course, as the area under that rectangle. So this was the magnitude of the area, and now here's the actual area in its vector notation. We've got a negative sign and a j hat indicating that it's pointing down in the j direction. So there's our little force vector notation bit of force. Okay, so we want to add up all those bits from x equals 0 to x equal L. So x equals 0, we're going to go L, capital L, length along the x-axis. And here's how we write that with an integral. Okay, we're going to define a force resultant, this right here, as the integral from 0 to L of all of the force elements. So f times dx, and f is going to change with every little incremental movement from 0 to L, and the integral helps us add those all up. So this is a continuous sum. This kind of big sloping S, just think of it as a continuous version of the summation symbol that you're probably used to. Okay, and now we've plopped in this this next expression right here. We've added the vector components of it. We've got this pointing in the j hat direction. We've got a negative sign to indicate it's pointing downward. And I've added the function notation for f, just to remind ourselves that this is some function of x. It isn't a constant, it's some function. And that we are integrating with respect to x. So in an integral, it's very important to know what you're integrating with respect to. Because what you're going to do is you're going to look for a function that if you took the derivative with respect to x, you'd get this. So that's important for calculating it. And it's also important for knowing what direction we're adding up along, because you might have to integrate in a couple of directions. You might have to add up all the contributions in, say, the y and the z, in case you have a full surface or a body, which is pretty easy. Just keep track of what you're integrating with respect to. This gives you a lot of power. Okay, if we want to look at moment due to just our big F sub r, our force resultant, once we calculate this about the origin, okay, we just take the cross product, and it would depend on where that force resultant ended up being. So once we completed our integral and we got an expression for F sub r, which is going to be a single number, when we integrate from a definitive point to another point, we end up getting a single number. So we'll have a single value for F sub r. We're going to know it's pointing downwards in the y direction, but we don't know where we would need to place it. The way we do that is to look at the effect of equivalent moment. So we're going to go back to that concept of equipollent force systems. This single resultant force vector placed at x sub r is going to be equipollent or equivalent to this whole distributed crazy load in terms of having the same effect with respect to force and moment on the entire rigid body. Only the whole body. If we end up cutting this up later on and wanting to look at internal forces, that doesn't hold. But right now we're just looking at the whole body. So equipollent force system. Crazy distributed load, continuously varying, is going to be equipollent or equivalent to a single force applied at a very particular location. Okay? So let's look at our single force system. We've already calculated our F sub r by evaluating an integral. So let's just assume that's an integrable function. We got our number, we know where it's pointing. So now we want to look at moment due to that. Okay? Well, we can define the moment of F sub r about the origin with our good old cross product. So r cross f, in this case r, is a radius vector pointing in the positive x direction to the location at x sub r where we're going to apply f sub r. So that's our moment expression. And the nice thing is these are orthogonal. So that's an easy cross product. Our sine of theta is 1. So all we need to do is multiply the two magnitudes. And we already have the magnitude of f sub r. Okay. So let's just write these two expressions back in terms of the integral, and let's write a radius vector with the proper unit vector. So x is going to go from the origin to the line of force of our resultant force. So it's going to be in the I hat direction. So we would write that vector as x I hat, and we're going to cross it into our resultant force, which we got by integrating this expression. So if we wanted to go back to our little tiny bit of force, this is how we would describe it. We know how to describe the whole one, but if we want to take the next step and say, well, what about this little tiny bit? Well, that little tiny bit of force, and this is really key, that little tiny bit of force induces a little tiny bit of moment about the origin. And we can define it the same way we define the resultant one, just with a cross product. So say we have some value x back to that's the x position of our little bit of force that we just evaluated here. So we can do the same thing with our little bit of force that we did with the resultant. You know, r cross f. But this time the r is just some x. We don't know what it is. It's some x, and it's going to be every x when we add them all up. And then our little bit of force is this expression that's inside our integral. Negative f sub x dx. So there's our area under our little rectangle at wherever it's positioned, however high it may be. It's in the y direction, and it's pointing down. So I can make a cross product of those two things. So I can just do x sub I cross this expression. I hat cross j hat is k hat. I retain the negative, and now I just have the two magnitudes multiplied together. So this negative x times the function of x, which defines my distributed load, dx, which is the width of my little bit of length pointing out of the paper, k hat direction, so it's pointing straight at us. This is a little bit of moment, a bit of moment. So it's an infinitesimally small moment or torque about the origin due to this particular value of our distributed load, which corresponds to that particular position, acting over this infinitesimally small length or width of our beam or our x-axis. So here is a bit of force that we're going to add up over 0 to L, and here's a bit of moment. And to get the total moment, we're going to add it up the same way. We're going to add up all these bits of moment from x equals 0 to x equals L. So we're going to do that right here. So we're going to say the moment of the resultant of that force distribution about the origin, so that's what that subscript means, due to force resultant about the origin of O, we've got a vector, is going to be negative k hat, so we took that right from here and here, and then we're going to add up everything in this magnitude expression with an integral. So we're going to add up all these bits of moment from x equals 0 to x equals L, and that's what this integral does for us. Now we got a different function though. Now we have x times f of x. So you're going to calculate this integral differently. So you're going to find the expression for which, if you took its derivative with respect to x, you'd get x times f of x. And that'll of course totally depend on what f of x is. It could be a constant, it could be a line, it could be a parabola, it could be a sine function. It totally depends on the nature of the distributed load. But now if we know what that function is, and we can do the integral, we know what the moment due to that distributed load is about the origin. So that's pretty much everything you need to know to get that. And likewise, we can use this plus this, so we can use the summation of all the bits of moment and the summation of all the bits of force to actually get our x sub r, our position of our force resultant, because the sum of the moment equals the moment of the sum. So we're going to use that definition of moments to equate our integral expressions to what we would get here if we just had a single force resultant. So let's just kind of walk through that. Okay, let's step through that. So we're going to say here's our moment expression that we got by adding up all the bits of moment, and we know that that's equal, because we're talking about an equipollent force system, that's equal to x sub r, which is our radius vector to our single action force resultant, cross f sub r, big F. This is our single resultant. That's going to be equal to this integral we just calculated. That's because, you know, we get that from them being equipollent. So we can drop that in based on the integrals, or we can drop in expressions that we just derived with our integration. So we're going to go x sub r I hat. We're going to leave that there because we're looking for that. We know we crossed it into f sub r. Well, f sub r is this, which you just calculated up here. So there's that. And your moment is what you just calculated here. So we'll just put that there. Now we can divide both sides because we know that the sine theta of this cross product is 1, so we can just work with this as scalars basically. So we can get rid of the cross product and just go to a multiplication of the magnitudes. So here our x sub r becomes just its magnitude, and that's, again, that's this position of the force resultant we're going for. Okay, so we're going to multiply that by the expression we got for our force resultant. We already did this integral, and we're going to set that equal to the integral expression for moment that we already calculated, and all we have to do is divide them, and that will be your position of your force resultant. So you have applied the definition of moment, and you have added up the contributions of a distributed load, in this case force per unit length, and you've added up those contributions over the entire length of application to get a total force resultant. Then you've looked at the moment due to each little bit of that force distribution, and you've added up all those bits of moment using this expression over the entire length, and then divided them. Sum of the moment equals the moment of the sum to get your x sub r. So you can take this whole crazy distributed load and say, I can write an equipollent single force acting at a particular location that has the same effect on, if this were a little beam, this whole rigid body as the distributed load. And it's much simpler to work with if you want to put it into equilibrium. So that's the main secret there. So let's do an example with a real function that we happen to know. Before we jump into that though, big important note that you won't need right now but will be dead useful later on. The scalar quantity that we just defined, this x sub r, is also known as the centroid of the particular area under f sub x over the length that we've defined. So this formula that we just derived for ourselves actually also happens to be the formula for the centroid of this crazy body, if we considered it to be a shape. So we literally just defined the definition of a centroid and also gave ourselves a great way of writing a resultant force vector and position of that vector for a distributed load. So twofer. So we just defined the definition of a centroid. So you can use the same concept later on when we start calculating centroids of crazy shapes and load distributions. Okay, so we're going to just step through a quick example here. Actually, it's not so quick, but this is a general one. So someone has a concrete ramp, and it has a weight given by some function, and the function is 0, at the beginning of the ramp, and it's equal to P sub L. So that means P is usually a distributed load, or Q are the common symbols for it, at some length L, and that's at position B here. So this triangular force distribution represents the load per unit length of this concrete. So here's like a porch, and here's the grass over here, and this is a concrete ramp. And because weight is dependent on volume at a given uniform density, we'll assume that the ramp is the same width everywhere. So literally, its weight per unit length going from the grass to the porch is a function of its height. So that's what made this a linear function. The load distribution is linear with the height of the ramp. So literally, its physical dimensions match its load distribution. That's pretty nice. So we're going to slap a coordinate system on here just to keep our vectors straight and make sure we don't make a sign error. So I hat is in the direction of the increasing load going from the grass to the porch, and then j hat is the height of the ramp in any given place. So someone wants us to find the magnitude and position of the force resultant from the concrete weight in terms of P sub L and B. And so P sub L is the weight per unit length right at the top where the ramp is the tallest, and B is the length of the ramp from where it hits the grass up to where it attaches to the porch. Why would you need to know this? One of the reasons might be that you didn't compact the soil underneath this very well, and you might need to calculate bearing strength of the soil, and you might be concerned that this might rotate literally as it sinks into the soil, and for that you would need to know where the resultant force is, because you'd start looking at the pushback of compacted soil and make sure that it's equivalent from a moment standpoint. This you could achieve static equilibrium with the normal force of the soil. So far, normal force of all of our surfaces that we've looked at has always been as much as is needed. It's equal to the weight or other downward force. But if you're talking about something like soil or some kind of deformable body, that isn't always true. So that might be a practical reason why you would want to do this calculation. You might be working with a geotechnical engineer who asks this, and you might be asked to provide that input to him or her. Okay, so we can do this using the procedure that we just derived for ourselves. Okay, step one, we need a continuous expression for that distributed load, and that usually goes by the term Q. Q is your distributed load, so that's kind of your starting point for all this integration. So it's a line. So we all took algebra, so we know how to make a line function. We have a y-intercept at, we're going to call x equals 0 this beginning point of the ramp. So we have a y-intercept, which is great. So our load distribution is 0 when y is 0, and now we need a slope, y equals mx plus b, right? So we know that at point A, we've gone up P sub L and we've gone over B. So the slope m, or slope of our line, is P sub L over B. So we could write a load distribution function, f of x equals mx plus b. B is 0, so an m is P sub L over b. So our function that we're going to end up integrating, our load at any per unit length at a length, is this constant times our length. Where are we on the ramp? Okay, so let's define a bit of force. So here's our width of any given little force element, and here's our force per unit length, and we know it's pointing down in our j hat direction that we just defined, and let's add them up from 0 to b, from our x equals 0 at the beginning of the ramp to our length b, where we're not concerned anymore, not attached to the porch maybe. So we'll integrate that function. So those of you who who are interested in learning to integrate, here's a step through a very easy integral. This is a constant times a variable, so this is a polynomial. We're going to integrate with respect to x. So what we're looking for is what function would we start with such that if we took its derivative with respect to x, we'd get this. We kind of got two things going here. First, we have our power rule. So we're going to need to take the derivative of something that looks like an x squared, because when you take the derivative of x squared, we drop one power and get x to the first. And then we know that that exponent comes down in front when we take the derivative. So we want that to not be there because it's not there here, so we plunk a 1/2. So this expression in these parentheses, if we took the derivative of this 1/2 x squared with respect to x, the 2 would come in front, multiply by the 1/2, we'd get 1, and then we would subtract 1 from that 2 and get x to the first, which is what we have here. So the integral of x with respect to x is 1/2 x squared. Constants just stay there, right? Because if I take the derivative of something multiplied by a constant, the constant just stays. So this negative p sub l over b just stays. It's a constant. Okay, so here's our integral. We have now added up. We have a continuous expression for the total weight. And now it just depends on what fraction of this ramp do we want to consider. And that's where our limits of integration come. We could stop this integral at any x and get the force due to this bit or this bit, but we want the bit from 0 to b. So these are what are known as limits of integration, and we bring them back over in this expression. And a common standard notation that says I've already integrated a function and now I'm ready to plug in my limits is this great big old square bracket. When you see that notation with these same limits that you saw over here on the original integral, this tells you I have integrated, this is the resultant integrated expression. Now I'm going to evaluate it between these limits. And the magic here is to evaluate this expression between these limits. All you have to do is plug the upper one in, evaluate it, plug the lower one in and evaluate it, and subtract the two. And it is always upper minus lower. So you'll have a sign there. Okay? So if we plug in b for negative pl over b times 1/2 x squared, we're going to plug b in for x. We end up getting a 1/2 b squared that we're going to multiply by the negative p sub l over b. We're going to cancel one of the b's, and we're going to end up with this expression. If we plug 0 in and subtract it, everything in this expression is multiplied by x, so when you put a 0 in for x, you get 0. So here's our force. And you will notice this looks very similar to the area under a triangle. So we just did a little confirmation of our 1/2 base height formula for a triangle area. There you go. P sub l is the height, b is the base, and we have a 1/2. So we sort of incidentally defined and derived the area of a triangle while we were at it. Kind of nice. Okay, now we want to do the same thing for moment. And so we're going to define a moment element, a little bit of moment. So how did we do that? We take our bit of distributed load, or our distributed load at a point, and we're going to make it a bit of load by adding a dx, and then we're going to give it a radius. So basically it's the same as this expression multiplied by x. So here's our bit of moment in this expression. And we're going to add up all the moment bits from 0 to b. And so we're going to use the same rules of integration. And this time we've ended up with an x cubed. So if we back check ourselves, if I took the derivative of this with respect to x, of course, I would subtract 1 from the exponent, and then that 3 would come down in front, become a 1, and I would be left with negative p sub l over b times x squared, which is what I have over here, because I have an x and an x, so I have an x squared. So I evaluate this integral between its limits. The lower limit of integration, which I would subtract, is 0 because everything's multiplied by 0. I plug in capital B for x, so I'll end up with a b cubed, and then I'll divide a b, so I end up with 1/3 p sub l b squared over 3. And if you have looked at a center of mass table, or centroid table actually, the centroid of a triangle is located 1/3 of the way from the tall end, so it would be somewhere right about here. So it's 1/3 of the length coming from the tall end. So we just inadvertently we're going to when we do our division, we're going to inadvertently or deliberately maybe define the centroid of a triangle, and also know where that resultant P sub L B over 2 equivalent force is located with respect to the start of our ramp. Okay, so now we're going to apply the moment of the sum, which is this side, the x sub r, the position from x, reference to x equals 0 of our big force resultant is equal to the sum of the moments. Because now we're gonna drop in our expression that was the sum of all those little bits a moment. So I use x sub r, the magnitude. I know, because these are perpendicular, that I don't have a sine theta that is not equal to 1. It's 1, so I can just work with magnitudes. So I take my f sub r that I just derived here, and there it is. I know it's in the k hat direction. And I just evaluated this as right here, and I know it's in the k hat direction. These negative signs are going to cancel, and if I divide the unit vectors by each other, they effectively cancel, so I end up with a magnitude of my x sub r, and I have to remember that it's pointing in the I hat direction. So if I do my algebra, the 2 multiplies over here, I cancel the p sub l's, I cancel one of the b's, and end up getting, so you have a b squared and a b, so that cancels, I end up with 1b, and end up with 2/3 b. Now, quick check. B is in length units. A radius vector should be in length units, so that's one good check, as to when you're working with numbers, keep your units in these calculations. Moment should be in force times length, Newton meters, foot pounds. Force should be in newtons or pounds, force units, and position should be in length. Okay, so the resultant force of the concrete ramp is going to have magnitude of 1/2 p sub l times b downward, and we're going to put it at x equals 2/3 b. So 2/3 b referenced from this point. So it's right at the centroid of the shape that this force distribution makes. So now I have my data to hand off to the geotechnical engineer, and we'll make sure the ramp doesn't sag. Okay, we're going to take a pause here because these are a little bit long to go through, and we will pick this back up in another follow-on lecture and walk through how we would work this with a beam. This is something you're going to need to know for internal forces of beams, which are very important for eventual strength of materials determination. So you'll be providing initial input to someone on how to choose the right materials that have the right flexural strength. So this will be our very first beam setup. So we'll do that in the next example, and then we'll have a second example in the next one about how to break up a distributed load and maybe make it a little bit easier to evaluate as an alternative method. So we'll have 2 different variations on the same one next time. So we will see you then.